My name is Jennifer Van Saters, and today I'll be discussing our recent result on the rotational behavior in old stars. Now, rotational evolution in these cool stars is interesting because it's a potential stellar age diagnostic. These stars spin down as a function of time, meaning that there's a relationship between the surface rotation period and the age, and that if you can calibrate this period-age relationship well enough, you can go out, measure rotation periods for stars, and, in principle, obtain precise stellar ages for large samples of field stars. The technique is known as gyrochronology, and in the past it's largely relied on open clusters as calibrating sources. So an open cluster allows you to obtain a precise independent age for a group of stars. You can measure rotation periods for these stars and combine these two things to calibrate the period-age relationships. The problem with using open clusters is that the oldest open cluster to date to have measured rotation periods is only 2.5 gig-years old, meaning that the gyrochronology relationships are largely uncalibrated and untested for old stars. Now the Kepler mission changes this picture a little bit, because now we can do astroseismology for large groups of old field stars. And these astroseismology yields precise, independent ages, and you can also measure rotation periods for these stars based on the spot modulation that's present in Kepler light curves. And these two things together, independent ages and rotation periods, can be combined to calibrate the gyrochronology relationships and test the relationships for old stars. We selected a sample of 21 stars that are cool enough to have undergone substantial spin down on the main sequence, have well-determined astroseismic ages, spot modulation rotation periods, and spectroscopically determined compositions. We can compare the rotation periods that we observed for these stars to the rotation periods we would have expected them to display based on existing gyrochronology relations. Here I am comparing the observed rotation periods to those predicted using the models of Van Saters et al. 2013, but the patterns that we see here are present regardless of the period-age relationship we choose to use. This ratio of the expected to the observed period is greater than 1 if the star is rotating more rapidly than we would have predicted, and less than 1 if it's rotating more slowly than expected. Shown on the x-axis is the independently or astroseismically determined age. Shown here are the period ratios as a function of age for a narrow slice and effective temperature around solar. Stars from the open clusters M37, Praesepe, NGC 6811, and 6819 are shown in black, and the astroseismic targets are shown in color. We see a systematic tendency for the oldest stars to be more rapidly rotating than standard period-age relationships predict. None of the existing literature relationships can reproduce this systematic offset that we're seeing in the oldest stars. We postulate that what's going on is that the old stars are undergoing weakened magnetic braking. We use the Rossby number, defined as the surface rotation period divided by the convective overturn timescale, as a proxy for magnetic dynamo effectiveness. As stars like the Sun age, their Rossby numbers increase. And we postulate that above some critical Rossby number, magnetic braking ceases, angular momentum loss ceases, and the star stops spinning down. We fit for the critical Rossby number that best reproduces the observed rotation distribution. The gray shaded area shows the region of this diagram that stars obeying this weakened braking law should occupy. Furthermore, we see that such a model well describes and recovers the trends that we see in both cooler and in hotter stars. This observation suggests that the Sun itself may be on the cusp of an interesting transition in its magnetic braking behavior, because the critical Rossby number that we infer is very similar to the Rossby number of the Sun. Now in this picture we expect that stars should depart from the kind of traditional magnetic braking schemes at about roughly halfway through the main sequence lifetime, which limits the precision and validity of gyrochronological ages for these older stars, because here rotation period really serves as a lower limit on the age rather than a precise indicator of age. So our paper is available on the archive, and it's also public on the Nature website. And so if you'd like to see a more detailed discussion of our methodology, of discussion of the selection bias surrounding our sample, we encourage you to take a look. Thank you.